600 light-years from Earth, a planet circles a star almost identical to our Sun. Kepler-22b sits in the habitable zone, where liquid water can exist on a planetary surface. The planet is 2.4 times the size of Earth. Its year lasts 290 days. Surface temperatures hover around 72 degrees Fahrenheit. NASA confirmed its existence in December 2011. The first planet found in the habitable zone of a Sun-like star. The Discovery team used transit photometry, watching the planet cross in front of its star 3 times over 4 years. Every measurement suggested this world could harbor oceans. But Kepler-22b breaks the rules. A planet this size should be a mini Neptune, wrapped in thick hydrogen and helium. It should be hostile to life. Instead, it orbits at precisely the right distance, maintains the right temperature, and circles a star nearly identical to ours. The coincidences stack too high. Scientists call worlds like this super-Earths, but they have no equivalent in our solar system. We cannot study them up close. We cannot see their surfaces. We can only measure their shadows and wonder if something lives beneath clouds we will never photograph. This planet challenges everything we assumed about where life can emerge. If you find this fascinating, hit that like button and subscribe. We begin now. You can walk outside tonight and look up. If you're far from city lights, you might see 2,000 stars, maybe 3,000 on a perfect night. The Milky Way stretches overhead if the moon stays down. You can find Orion, the Big Dipper, maybe Jupiter, are bright and steady near the horizon. This is the sky humans have known for 50,000 years. Kepler-22b is up there too, right now, this second. You cannot see it. Not with your eyes, not with binoculars, not with most amateur telescopes. The star it orbits is a G-type yellow dwarf, similar in size and type to our Sun. It should be visible, but space is not just big, it is invisibly big. Even for Sun-like stars, even for systems that mirror our own, the distances swallow everything. Most of the universe that resembles us remains hidden in plain sight. The star is 635 light-years away. That is 3 quadrillion miles. If you started driving when the first cell divided on Earth billions of years ago, you would still be driving. You would pass the birth and death of entire species. You would drive through the age of dinosaurs, through the rise of mammals, through every human civilization, and you still would not arrive. 635 light-years means something else too. The light you detect from Kepler-22b today left that system 635 years ago, around the year 1385. The printing press did not exist yet. The Renaissance had not begun. Most of the world had never heard of Europe. The photons reaching our telescopes now began their journey before your family tree had a single branch you could trace. You are not looking at a planet. You are not seeing it as it exists now. You are looking at history traveling through space. That photon is older than your family name. It crossed the void for 6 centuries before touching a sensor in California. But this is the part that gets me. We found it, and we will never touch it. The star itself is 20% dimmer than the Sun, 25% lower in luminosity. That sounds minor. It is like comparing a 60-watt bulb to a 75-watt bulb. They seem similar until you live under one for a year, until you grow crops under one, until you try to keep a planet warm enough for liquid water. That 15-watt difference becomes everything. NASA discovered Kepler-22b in December 2011 using the transit method. The technique is simple in concept. Point a telescope at a star. Watch. Wait. If a planet crosses in front of that star from our perspective, the starlight dims. Just a fraction. Less than 1% usually, but enough to measure if your instruments are sensitive enough. A Kepler-22b dimmed its star 3 times over 4 years. 3 transits. 3 tiny dips in brightness, each one exactly 290 days apart. The consistency told astronomers everything. A planet was there. It had a year. It had a size. And it occupied the habitable zone. The distance to Kepler-22b means we are always looking backward. When astronomers confirmed the planet's existence, they were seeing it as it appeared during the 1400s. If someone on Kepler-22b aimed a telescope at Earth right now, they would see our planet as it was in the 13th century. They would see no electric lights, no radio signals, no evidence of industrial civilization. We would look quiet, perhaps lifeless. This creates a strange isolation. We can find these worlds, yet we can measure their size and orbit and temperature, We can calculate whether water might pool on their surfaces, but we see them only as they were centuries ago. Anything happening there now, any storm or season, or possible emergence of life, remains hidden behind the speed of light. By the time we see it, hundreds of years will pass. The star is ordinary. That might be the strangest part. Kepler-22 is not exotic. It is not a red giant or a white dwarf or a neutron star. It is a main sequence star, fusing hydrogen into helium, sitting comfortably in middle age. If you could visit it, you would recognize it. The light would feel familiar. The color would look right. You could almost imagine the sun in its place. But we cannot visit. We can only collect the ancient light and decode what it contains. And the transit method turns starlight into data, brightness into orbital mechanics, a brief dimming into the architecture of another solar system. The detective work happens here, in our time, using photons that are older than most nations. The dimming lasts hours. When Kepler-22b slides across its star, the light drops by a measurable amount. Scientists capture this dip. They measure its depth, which reveals the planet's size relative to the star. They measure its duration, which reveals how fast the planet moves. They measure the time between transits, which reveals the length of the year. All of this from a shadow, from a slight decrease in brightness that most instruments would miss. We found a world we cannot see, orbiting a star we cannot see, using light that left before the Renaissance. And from that light, but we learned it sits in the habitable zone. We learned it might have oceans. We learned it exists at all. That is where the questions begin. The detective work starts with geometry. When Kepler-22b crosses between its star and us, it blocks light. The star dims, not by much, just enough to measure if you're looking carefully from the right angle. This is the transit method. A planet reveals itself by casting a shadow across 600 light-years of space. Detecting a planet this way is like seeing a gnat cross a stadium spotlight from the parking lot, except the stadium is in another state. The dimming lasts only a few hours. The measurements must be precise enough to catch a change in brightness of less than 1%. 1%. And that's the difference between a star shining normally and a world the size of Earth passing in front of it. Each transit dip in starlight is a silhouette, the planet's shadow signature, written in missing photons. The depth of the dip tells us how large the planet is compared to its star. The duration tells us how fast it moves across the star's face. The time between transits tells us the length of its year. All of this from a shadow, from brightness measurements taken by sensors more sensitive than any human eye. Kepler-22b's star dims by a tiny fraction when the planet crosses. Scientists measured that fraction. They calculated the planet's diameter from it. They watched multiple transits and timed them. 290 days between each crossing. That's the orbital period, the length of 1 year on that world. And from the orbital period, they calculated the distance from the star. Physics connects these numbers. Kepler's laws turn transit timing into orbital architecture. The star itself is 4 billion years old. It has been burning since Earth was a molten ball. It's our sun's age twin, a middle-aged star with billions of years left. This matters because young stars are violent. They flare. They strip atmospheres from nearby planets. An old star is calmer, more stable, the kind of star where life might have time to begin. But here's something most people don't realize. The transit method only works if we happen to be aligned edge-on to the planet's orbit. Think about that geometry. If the planet's orbit is tilted even slightly from our perspective, it never crosses the star's face. We see the star shine steadily. No dimming, no shadow, no detection. We're finding planets by cosmic coincidence. Most planetary systems are invisible to us, not because they're too far away, not because our instruments aren't good enough, because we're watching from the wrong angle. The universe is full of worlds we will never detect this way. They exist. They orbit their stars. But they never cross our line of sight. We only see the ones whose orbits happen to be aligned with Earth. Pure chance. Imagine every solar system as a dinner plate spinning in space. We can only spot the planets on plates that are edge-on to us. All the plates tilted at other angles remain invisible. Their planets are just as real, just as present, but the geometry hides them. This means something profound. For every planet we detect by transit, there are hundreds we miss, maybe thousands. In Kepler-22b won the lottery. Its orbit is aligned, the star dimmed at just the right time. We happened to be looking. The spacecraft recorded the data. Scientists confirmed it wasn't a false positive, not a binary star system, not an instrument error. A planet, crossing its star every 290 days. The precision required is staggering. Kepler had to stare at the same patch of sky for years. It monitored over 150,000 stars simultaneously. It measured their brightness every 30 minutes. Any change, any pattern, any repeating dip that might be a planet. Most stars showed nothing, just steady light across years of observation. But some dimmed rhythmically, predictably. Those were the candidates. From those brightness measurements, we know Kepler-22b exists. We know its size. But we know its year. We know its distance from the star. We know the star's age and temperature. We even have hints about its atmosphere. When a planet transits, starlight passes through the outer layers of its air. Different gases absorb different wavelengths. The spectrum changes in measurable ways. Scientists can read chemical signatures in that filtered light. This is what the transit method gives us. Raw data, numbers, orbital mechanics, the basic architecture of a distant solar system extracted from patterns of dimming light. We cannot see the planet directly. We cannot photograph its surface. We know it only by the shadow it casts and the starlight it blocks. We know Kepler-22b exists and its basic statistics, but those numbers raise deeper questions. What kind of world is it? And if you could pick up Kepler-22b and drop it into our solar system, where would it go? Not in Earth's orbit. Closer than that, about 15% closer to the Sun than we are. It would sit between Earth and Venus, right in the middle of that gap, the Goldilocks parking spot. Not too hot, not too cold, at least not automatically. Its year lasts 290 Earth days. That's 25% faster than ours. Seasons would pass quicker. Spring would arrive sooner. Summer would end before you were ready. A childhood would be shorter by months each year. Old age would arrive faster. All on a calendar that doesn't match human rhythm. Everything slightly rushed, time moving just a bit too quick. But here's the part that rewrites everything we thought about habitable zones. A Kepler-22b sits closer to its star than Earth does to the Sun. By all logic, it should be hotter, maybe too hot. Venus is close to the Sun, and Venus is hell. But Kepler-22b could still be comfortable, mild even, because its star is dimmer than ours, cooler, less intense. Proximity doesn't determine habitability. The balance between distance and star brightness does. Venus isn't hell because it's close. It's hell because it's close to this star, our bright yellow furnace. Kepler-22b orbits a quieter flame. The math changes completely. The temperature on that world depends on three things: atmosphere, rotation, axial tilt. We don't know any of them for certain. What we have are possibilities. 3 different fates for the same planet. 3 entirely different worlds occupying the same orbit. First fate. A Kepler-22b has an atmosphere like Earth's. It rotates normally, maybe once every 20 or 30 hours. It has seasons. It has day and night in familiar rhythm. Under those conditions, the surface temperature averages 22 degrees Celsius, 72 degrees Fahrenheit, room temperature, comfortable. You could walk outside without a suit, breathe the air if the chemistry was right. This is the optimistic scenario, the one where the planet cooperates with our hopes. Second fate, no atmosphere, or such a thin one it barely matters. The planet still rotates, still has day and night, but without atmospheric insulation, the average temperature drops to -11 degrees Celsius. -18, if you believe some models. That's cold, well below freezing. Not impossible for life, but harsh, unforgiving, and a frozen desert lit by a dim star. This is the pessimistic scenario, the one where the universe doesn't give us what we want. Third fate, Kepler-22b has an atmosphere, but it's thick, crushing, rich in carbon dioxide, like Venus, a runaway greenhouse. Heat trapped in layers of gas so dense they turn the surface into an oven, 460 degrees Celsius. Hot enough to melt lead, hot enough to sterilize anything we'd recognize as life. This is the nightmare scenario, the one that looks habitable from space but kills anything that gets close. Same planet, same orbit, same star. 3 completely different realities. Which one is true? We don't know. We can't know from 635 light years away. All we have are measurements of size and orbit. The rest is modeling, guesswork, educated assumptions built on atmospheric physics and probability. There's another variable, rotation itself. How Kepler-22b spins changes everything about what it means to live there. It might rotate like Earth, a normal day-night cycle, axis tilted just enough to give it seasons. Summer in one hemisphere, while the other faces winter. That's the familiar option, the one our minds default to because it's what we know. Or maybe it tumbles. Axis tilted so far over it rolls like Uranus, poles pointing at the star for half the year, the northern hemisphere baking in constant daylight while the south freezes in endless night. Then 6 months later, they switch. Extreme seasons, radical temperature swings, a world where north and south mean something entirely different than they do here. Life would have to adapt to that. Migrate, hibernate, or die. Or maybe it's tidally locked. One face always pointed at the star, one face always dark, the same hemisphere baked in eternal noon while the other freezes in permanent midnight. No sunrise, no sunset, just a star that never moves and a night that never ends. It's like a rotisserie chicken that stopped turning, half charred, half raw. The only habitable zone would be the thin ring between the two, the terminator line, where day meets night, where temperatures balance just enough for liquid water. Everywhere else, extremes. We've found tidally locked planets before. They're common, especially around dim stars like Kepler-22, close orbits, gravitational pull strong enough to lock the rotation, one side always facing inward. The planet becomes a half-world, two zones, day side and night side, and maybe, if you're lucky, a narrow strip of twilight where something could survive. Each rotation scenario creates a completely different climate, different wind patterns, different ocean currents, if there are oceans, different places where heat and cold collide. A normal rotation spreads heat evenly. A tumbling axis creates wild seasonal extremes. A tidally locked planet concentrates heat on one side and cold on the other. The atmospheric dynamics don't even resemble each other. They're three separate physics problems, and we are 635 light-years too far away to check. We can't see the planet directly, can't watch it spin, can't measure how sunlight moves across its surface or whether it even has a surface. The data we have tells us it exists, tells us its size and orbit and the temperature of its star. But it doesn't tell us what kind of world it actually is, whether it spins in familiar rhythm or hangs frozen in tidal lock, whether its air is breathable or poisonous or absent entirely. Same planet, three possible realities, and we're standing here, looking at the data, imagining all three at once. Because until we get closer, until we build instruments powerful enough to resolve details across that distance, all three fates exist at the same time. Kepler-22b is a paradise, a frozen wasteland, and a hellscape, simultaneously, at least in our minds. The truth is out there, already real, already decided by physics that played out millions of years ago. But we don't know which truth we're looking at yet. The most exotic possibility, the strangest fate, the tidally locked scenario. That's the one that haunts the imagination. A world split in two, forever divided between fire and ice. Let's imagine the worst case, or maybe the most fascinating case. The scenario where Kepler-22b stopped spinning billions of years ago and locked itself into perpetual rotation. One face always toward its star, one face always turned away. This creates three distinct zones. The light side faces the star forever. Perpetual day, a sun that never sets, never moves across the sky, just hangs there at the same angle for eternity. Plants on this hemisphere could photosynthesize constantly, growing under a never-ending flood of starlight. They'd never sleep, never close their leaves for night, because night never comes. The energy would be relentless, but so would the heat. With no night to cool things down, temperatures would climb, and storms fueled by constant heating would rage without pause. The atmosphere would churn, water would evaporate, and without rotation to distribute that heat around the planet, the light side risks becoming a runaway greenhouse, hot enough to boil oceans, hot enough to strip away any chance of life. The dark side never sees the star. Eternal night. Temperatures plummet without starlight to warm the surface. Any water freezes solid. The atmosphere itself might condense into lakes of liquid nitrogen. This hemisphere becomes an ice tomb. Lifeless, right? That's what you'd assume. But Earth taught us something surprising about life in darkness. At the bottom of our oceans, kilometers below the surface where sunlight never penetrates, there are hydrothermal vents, cracks in the seafloor where superheated water rich with minerals pours out. And around those vents, life thrives, not through photosynthesis, through chemosynthesis, bacteria that extract energy from chemical reactions, from sulfur and methane and heat. They eat rocks, essentially, and they form the base of entire ecosystems. Tube worms, crabs, fish, all living in complete darkness, powered not by a star, but by the planet's own internal heat. Here's the surprise. The dark side of a tidally locked world wouldn't necessarily be dead. It could have its own biosphere, creatures living in eternal night, feeding on geothermal energy seeping up from the planet's core, not dependent on starlight at all, just heat and chemistry. And if that's true, then Kepler-22b could host two completely separate biospheres that never interact. One hemisphere powered by starlight, one powered by planetary heat. Two different evolutionary paths, two different forms of life on the same world. But between these extremes lies a third zone, the terminator zone, the narrow band that circles the entire planet where light meets dark, permanent twilight. Imagine living there. The star sits fixed on the horizon, not rising, not setting, just glowing there in endless sunset. Yet you could walk north and feel the temperature climb, degree by degree, until the heat becomes unbearable. You could walk south into deepening cold until ice covers everything. But right along that ribbon of twilight, temperatures remain stable. Not too hot, not too cold. Water stays liquid. The atmosphere doesn't boil away or freeze solid. This zone would experience the most stable conditions on the entire planet. Think about what that means for life. The terminator zone becomes the sweet spot, the habitable ring, liquid water pooling in the twilight, organisms adapting to dim but constant light. Maybe photosynthesis happens here too, just slower, optimized for perpetual dusk. The ecosystem would be strange. Plants that evolved to maximize energy capture from weak starlight. Animals that never experienced the cycle of day and night. And no circadian rhythms, no seasonal changes. Just the gradient from light to dark stretching across the landscape. The width of this zone depends on the atmosphere. A thick atmosphere with strong winds could transport heat from the light side and cold from the dark side, widening the habitable band. Maybe the terminator zone wouldn't be a thin ribbon after all. Maybe it would spread, become a broad temperate region wrapping around the planet, kilometers wide, maybe hundreds of kilometers. Enough space for complex ecosystems to develop, forests in perpetual twilight, rivers fed by melting ice from the dark side, weather patterns driven by the eternal temperature gradient. Or maybe the atmosphere is thin, maybe heat transport is minimal. Then the terminator zone collapses to a narrow strip, a few kilometers wide at most, a life clinging to that tiny border between fire and ice, crowded into the only place water can exist as a liquid, the only place temperatures allow chemistry complex enough for biology. We don't know which version Kepler-22b represents. Don't know if the terminator zone is a broad belt or a knife's edge. Don't know if life would find it hospitable or marginal. But among the three zones, this twilight border offers the best chance, the most likely candidate for sustaining complex ecosystems, for liquid water oceans, for atmospheres that stay stable over geological time. All three zones could theoretically support life, just radically different types. The light side, with its photosynthetic organisms burning under a motionless sun, the dark side with its chemosynthetic creatures feeding on the planet's internal heat. The terminator zone with its twilight ecosystems balanced between extremes. Three biospheres, three evolutionary experiments, all running simultaneously on different parts of the same world. That's assuming tidal locking is the reality. Assuming this planet did stop spinning. Assuming we've guessed correctly about its fate based on incomplete data from 600 light years away. But if it is tidally locked, if those three zones exist, then the question becomes specific, focused. Not whether life could exist on Kepler-22b, but what kind of life? What adaptations? What strange forms would evolution produce in perpetual twilight? What would creatures look like that never saw a sunrise? Kepler-22b has a second unpleasant surprise. After the tidal locking, after the climate extremes, there's the gravity. 6 times Earth's, not a subtle difference, not something you'd adjust to with time. 6 times Earth's gravity means every step feels like carrying 5 copies of yourself on your back. Standing upright would crush your spine. Your heart would struggle to pump blood. Your lungs would labor under their own weight. Think about what that means for native life. Any creature evolving under those conditions wouldn't look familiar, couldn't look familiar. Earth's body plans don't work at 6G. Our skeletons are built for our gravity. Our muscles developed their strength against 1G of resistance. Double it, and we'd struggle. Triple it, and most land animals would collapse. 6 times, we're talking about a world where every biological structure faces crushing weight from birth. The planet's mass makes this inevitable. At 36 times Earth's mass. That much matter pulls hard on everything near it. Life would have to adapt or die. Evolution doesn't compromise on physics. So what does adaptation look like? Start with the basics. Height becomes a liability. Tall creatures concentrate too much weight on too few support points. The longer your body, the more stress on your spine, your joints, your internal organs. Everything wants to compress downward. Gravity wins unless you engineer around it. Life would stay low. Creatures hugging the ground like reptiles. Short bodies with powerful, thick-boned skeletons. Muscles dense and compact. No room for inefficiency. Every gram of tissue needs structural purpose. But there's more. 4 legs distribute weight better than 2, but 8 legs work even better. Multi-pedal creatures spreading their mass across many contact points. Picture furniture with many legs instead of 4. More stable. Less pressure on each individual support. A bear-sized animal on Kepler-22b might walk on 8 short, thick limbs, or 10, or 12, whatever number evolution settles on to keep weight distributed and organs intact. The real innovation would be external support. Exoskeletons made of something like chitin or calcite, hard biological material, forming shells around soft tissue, not just for protection, for load-bearing. The exoskeleton carries weight like architectural support beams. Biology becomes engineering. The shell prevents organs from compressing under their own mass, keeps lungs from collapsing, keeps blood vessels from rupturing. It keeps everything contained and functional despite the relentless downward pull. These wouldn't be delicate shells like Earth insects have. They'd be thick, flexible enough to allow movement, but rigid enough to resist compression. Maybe segmented like armadillo plates, maybe layered like geological strata. Dense composite materials that evolution spent millions of years perfecting through trial and error and mass extinction events. Flight would be virtually impossible. Birds on Kepler-22b would be crushed before liftoff. The sky would be empty of wings. Actually, that's not quite right. Let me try again. The sky wouldn't be empty. Insects might still manage it, staying tiny. Mass increases with volume, but wing surface area only increases with the square. Stay small enough, and the math still works. But nothing bird-sized or larger. The sky belongs to the small. Plants face the same challenge. Trees as we know them couldn't exist. Not tall ones. The structural requirements to support height under 6G make vertical growth impractical. Any plant taller than a few meters would need trunks impossibly thick. The resources required wouldn't justify the height gained. Evolution favors efficiency, so vegetation stays low. Stout plants with thick stems and deep root systems. Massive roots anchoring against gravity and providing structural reinforcement from below. The landscape would look compressed, flattened, like someone took an earth forest and crushed it under a hydraulic press. But underwater, the rules change completely. Buoyancy counteracts gravity. Water supports weight that air cannot. A creature weighing tons on land becomes nearly weightless, submerged. That's where gigantism becomes possible. Large bodies spreading through ocean depths. Massive organisms that could never support themselves on land but thrive in water where physics grants mercy. The contrast would be stark. Terrestrial life small and compact and heavy-boned. Aquatic life potentially enormous. 2 different worlds occupying the same planet. The ocean as refuge from gravity's tyranny. Actually, that's not quite right. Let me try again. Tidally locked doesn't mean frozen. It means something stranger. Creatures adapted to crushing weight might also need adaptations for temperature extremes. For perpetual day or perpetual night, or the twilight between them. Gravity shapes their structure, but climate determines where they can live. The 2 pressures working together, filtering possibility. Complex life could exist on Kepler-22b. The physics allow it. The chemistry permits it. But that life would look alien to us. Short, armored creatures moving on many legs. Dense, flexible shells protecting soft interiors. Bodies engineered by evolution to survive under weight that would kill us instantly. No birds, no tall animals, nothing reaching toward the sky. Just low, heavy, relentlessly efficient biology. Life that traded grace for survival, beauty for function. But before we imagine what ecosystems built from these components might look like, we need to understand the stage they'd occupy, the actual terrain. What does geography look like on a tidally locked world 600 light-years away? Geography on Kepler-22b doesn't look like Earth. Picture a globe covered entirely in water. No continents, no islands, just ocean wrapping around the whole planet with nowhere for waves to break. The Pacific, but circling the entire world. That might be what we're dealing with. The planet is 2.4 times larger than Earth. That's substantial. More than double the diameter. You might expect deeper oceans to match. More water filling deeper basins. Trenches plunging even farther than Earth's deepest points. But that's not what the models suggest. The average ocean depth on Kepler-22b might be just 160 feet. 160 feet is the height of a 15-story building lying on its side underwater. Shallow. Really shallow. On Earth, the average ocean depth is about 12,000 feet. Our oceans plunge to 7 miles down in the deepest trenches, places where the pressure would crush a submarine like a tin can. Kepler-22b's oceans wouldn't even cover a skyscraper. You could dive to the bottom with scuba gear in many places. This is the surprise. A planet 2.4 times Earth's size could have oceans only half as deep as ours. Larger doesn't mean deeper. It depends entirely on how much water exists and how it spreads across the surface. Think of it like wrapping Earth in a shallow bathtub. More surface area to cover, but the same amount of water spread thin. Kepler-22b might be a shallow global sea rather than deep Earth-like oceans. The implications are strange. 160 feet of water creates a fundamentally different environment than Earth's oceans. Their light penetrates all the way to the bottom in most places. No abyssal zones, no midnight depths where bizarre creatures hunt in permanent darkness. The entire ocean would be in the photic zone, where sunlight reaches. Warm at the top, still warm at the bottom. Waves would behave differently too. On Earth, deep water allows waves to build massive energy. Tsunamis crossing the Pacific gain power from thousands of feet of depth beneath them. On Kepler-22b, waves would feel the bottom constantly. They'd break and reform and dissipate quickly. The ocean would churn, but never really settle into the deep rhythms Earth's oceans follow. Climate is where shallow oceans matter most. Water stores heat. It absorbs energy during the day and releases it slowly at night. Earth's oceans are the planet's thermostat. They moderate temperature, preventing wild swings between scorching days and frozen nights. This is the callback to earlier climate scenarios. The reason Kepler-22b might remain habitable despite its unique conditions. A shallow global ocean still performs this function, maybe even better than Earth's in some ways. With water covering the entire surface, every part of the planet benefits from thermal regulation. No desert interiors baking under endless sun. No frozen tundra cut off from moderating ocean currents. The whole world stays within a narrower temperature range. Stable, predictable, but 160 feet of water stores less total heat than Earth's deep oceans. The thermal mass is lower. Temperature swings might happen faster over shorter timescales. Storms could brew quickly as surface water heats and cools. Their weather patterns might be more chaotic, less predictable, even as the overall climate remains stable. It's a different kind of equilibrium. The real question is land. Does any exist at all? With an average depth of 160 feet, there could be shallow areas, underwater plateaus rising to within 20 or 30 feet of the surface, maybe even occasional islands breaking through in a few spots. But land would be scarce, precious. Most of the planet would be featureless ocean as far as any observer could see. This creates a problem for life. On Earth, life likely began in shallow pools, tidal zones where water mixed with minerals from land, places where chemistry could concentrate and experiment. A completely ocean-covered planet has no tide pools, no beaches, no river deltas carrying nutrients from eroding mountains, and just water meeting water. Life might still emerge in the oceans themselves. Deep-sea vents on Earth support entire ecosystems without sunlight, but those ecosystems are small and isolated. Complex life, diverse ecosystems, the kind of biology we think of as vibrant and teeming, usually needs more. It needs boundaries, gradients, places where different environments meet and create opportunities. Kepler-22b might have those boundaries in the water column itself, shallow enough that the entire ocean has layers of temperature and chemistry and light. The top 10 feet different from the middle, 80 different from the bottom 70. Invisible borders creating ecological zones stacked vertically instead of spread horizontally. Life adapted to specific depths the way Earth's life adapts to specific altitudes. But no land complicates more than just the origin of life. It complicates any dream of colonization. Humans need solid ground. We build on it, grow food in it, extract resources from it. A world with no land is a world with no foundation. You'd have to float forever. Massive platforms tethered to nothing, drifting on shallow seas. Every structure artificial. Every resource imported or synthesized from seawater. The ocean itself might provide some materials. 160 feet of water covering a rocky planet means a seafloor everywhere. Mining the bottom would be easier than on Earth. where the deepest resources lie miles down under crushing pressure. Here, you could reach the seabed with simple equipment, extract minerals, anchor structures, but you'd still be living on top of water, not solid ground, always moving, and never still. That's the paradox of Kepler-22b's geography, a planet that might be habitable, but offers no habitat in the traditional sense. Oceans that regulate climate beautifully, but provide no land for life to colonize. A shallow global sea that's easy to access but impossible to escape. The physics work, the chemistry permits it, but the geography presents challenges we've never faced. Speaking of challenges, what would humans actually encounter if we somehow reached this world? What would standing on a floating platform 600 light-years from home really feel like? We don't really know if Kepler-22b has oceans. That's the honest answer. We're guessing based on size and distance. The temperature looks right. The star delivers warmth without burning. But whether water actually exists there, whether it forms shallow seas or deep abysses, or none at all, that's speculation dressed up in math. The dream of colonization assumes water. It assumes a surface we can reach. It assumes we could stand there and look up at an alien sky. The reality is far more brutal. Gravity would crush you. Your body weighs what it weighs because Earth's gravity pulls on your mass with a specific force. On Kepler-22b, that force multiplies by 6. A person weighing 175 pounds on Earth would weigh 1,050 pounds there, the weight of a grand piano strapped to your skeleton. Every bone bearing a load it never evolved to handle, every joint compressed beyond its design limits. Your heart would strain to pump blood upward against 6 times the resistance, yet your lungs would labor to expand your ribcage against 6 times the pressure. Standing upright would become nearly impossible. Your legs would buckle. Your spine would compress. The simple act of lifting your head to look forward would require muscular effort you don't possess. Think about carrying someone on your shoulders, the strain in your legs, the burn in your thighs, the desperate urge to set them down. That's one additional person. Kepler-22b adds 5 more, constantly, forever. The spacesuit makes it worse. An EVA suit weighs 290 pounds on Earth. That's heavy, but manageable with training. On Kepler-22b, that same suit weighs 1,700 pounds, heavier than a horse, and you're expected to walk. The combined weight of your body and equipment would exceed 1 ton. Your movement wouldn't just be difficult, it would require mechanical assistance. Exoskeletons powered by motors strong enough to lift industrial equipment. Your muscles couldn't do it alone. The suit designed to protect you becomes a prison you can barely operate. Even with mechanical help, every step would be a calculated risk. This is the part that gets me. The real danger isn't just standing, it's falling. On Earth, gravity accelerates falling objects at 32 feet per second squared. On Kepler-22b, that rate multiplies to 192 feet per second squared. You fall 6 times faster, reach terminal velocity in a fraction of the time. A drop that would take 3 seconds on Earth takes less than 1 second there. You'd hit the ground at highway speeds before your brain registered you were falling. And consider a fall from 160 feet. On Earth, that's roughly the height of a 15-story building. Fatal, certainly, but the fall takes about 3 seconds. Emergency systems might deploy. You'd have time to react, even if the outcome remained the same. On Kepler-22b, the same 160 feet disappears in under 1 second. You'd reach speeds near 120 miles per hour, hitting water at highway speeds. Your bones would snap like chalk. There would be no recovery, no emergency response, just impact and silence. Tripping means death. Walking across uneven terrain becomes Russian roulette. A crack in the ground, a loose rock, a moment of imbalance. Any of these could send you down. The exoskeleton might keep you upright under normal conditions, but it can't predict obstacles, can't react faster than physics. One mechanical failure, one power glitch, one servo malfunction. You'd go down and never get back up. The weight would pin you. Lifting yourself from prone to standing requires core strength and leverage. Under 6 times your weight, that leverage vanishes. You'd lie there, pinned by your own mass, waiting for rescue that might never come. Climbing would be impossible. A ravine on Earth might be escapable. Difficult, exhausting, but possible. On Kepler-22b, vertical movement becomes a fantasy. Each handhold has to support over a ton. Each pull upward fights 6 times the force. Your fingers would slip. Your grip would fail. The rock itself might crumble under stress it never experienced. There's no getting back up from a fall into a crevasse. No climbing to safety. You'd be stuck at the bottom, crushed by weight, until resources ran out. The planet itself would reflect this brutality. Plant life, if it existed, would grow short and stout, thick stems to support leaves against crushing weight. Nothing tall, nothing delicate. Trees would resemble stumps. Grasses would hug the ground. Every organism shaped by the same merciless force that would destroy human bodies. Evolution on Kepler-22b would favor low profiles and structural reinforcement. Anything reaching upward would collapse under its own mass. The exoskeletons might let you stand, might let you walk slowly across flat terrain, but they don't solve the fundamental problem. You're still a human body designed for one gravity trying to function in 6. Your cardiovascular system would struggle, blood pooling in your legs, your inner ear sending confused signals, balance compromised, fatigue setting in after minutes instead of hours. The exoskeleton carries the weight, but your organs still experience the acceleration. Your blood still weighs 6 times more. Your brain still sits in a skull pulled downward with 6 times the force. But long-term habitation becomes a medical nightmare. Bone density would increase, but not fast enough. Muscle tissue would tear under loads it never adapted to handle. Joint cartilage would wear down rapidly. You'd age faster, deteriorate quicker. Even if the technology kept you mobile, your body would rebel against the environment. Months on Kepler-22b might age you years. The damage might be irreversible, even if you returned to Earth. The floating platforms imagined in the previous section assume you could work on them. Assume you could maintain structures, operate equipment, live something resembling a normal life. But every task becomes exponentially harder. Lifting tools, climbing ladders, moving cargo. Simple maintenance that takes minutes on Earth would take hours there. Exhaustion would be constant. Injuries frequent. The colony wouldn't just be difficult. It would be a test of human endurance, with no guarantee anyone could pass. Your journey might end as soon as you exit the shuttle. One step onto the surface, one moment of mechanical failure, one loss of balance. The dream of standing on a new world crashes against the physics of that world. Kepler-22b might have the perfect temperature, might have liquid water, might tick every box on our habitability checklist. But habitability requires more than chemistry and climate. It requires gravity we can actually survive, and this world might simply be too heavy for human bodies to endure. Even if we wanted to reach it, even if we solved every other problem, could we ever actually get there? The gravity problem is formidable, but even if we solved it, even if we engineered bodies or technologies that could withstand 2.4 times Earth's pull, there's another problem, one that dwarfs everything else we've discussed: distance. Kepler-22b sits 635 light-years from Earth. That number gets thrown around so casually in astronomy that it loses meaning. 635 light-years, like it's just an address, just a cosmic zip code. But let's translate that into something real. A light-year is how far light travels in 1 year. Light moves at 671 million miles per hour. Nothing in the universe goes faster. And even at that incomprehensible speed, it takes 635 years for light to cross the void between us and that world. The Parker Solar Probe is the fastest object humanity has ever built. Yet it's screaming toward the sun right now at 430,000 miles per hour. That's 119 miles per second. You could cross the entire continental United States in less than half a minute at that speed. It sounds impossibly fast because by human standards, it is. But in cosmic terms, we're barely moving. The Parker Solar Probe travels at 0.064% the speed of light. Not 6%, not even 0.6%, 0.064%. It's like comparing a jet plane to continental drift. The jet feels fast until you realize the continents are moving slower than your fingernails grow. And somehow, that's the comparison we're dealing with. We think we're making progress on space travel. We've built rockets that can escape Earth's gravity, or probes that can visit other planets, spacecraft that have left the solar system entirely. But against the scale of interstellar space, we're standing still. Let's do the math. If we could point the Parker Solar Probe directly at Kepler-22b and maintain that maximum speed for the entire journey, how long would it take? 992,000 years. That's longer than Homo sapiens has existed as a species. Every step of human evolution, every invention, every civilization, every war, every discovery. The entire story of our species, from the first stone tools to quantum computers, would fit inside that journey with time to spare. You'd need a ship that outlasts the entire human story, and then you'd need it to last longer. The probe would arrive at a dead world orbiting a dead star. carrying the fossils of whatever launched it. That's with our fastest technology. What about theoretical propulsion systems? The concepts that exist on paper but haven't been built yet? Nuclear pulse propulsion, nuclear fusion drives, technologies that would require decades of development and resources we can barely imagine committing. The most optimistic projections suggest these could reach 10% the speed of light, 62 million miles per hour, 100 times faster than anything we've ever built. At 10% light speed, the journey to Kepler-22b would take 6,350 years. Think about what that means. 6,350 years ago, humans were just inventing writing. Sumeria was rising in Mesopotamia. The pyramids hadn't been built yet. Every civilization that has risen and fallen since then, every empire, every language, every religion, would fit inside the journey time. You'd leave Earth before recorded history began and arrive in time to start it again. And that's the best case scenario. That's if we solve nuclear propulsion. If we build ships that can sustain those speeds without disintegrating. If we develop life support systems that can function for millennia. If we figure out how to keep a crew alive across 200 generations. If we solve radiation shielding and cosmic debris impacts and 1,000 other problems we haven't even identified yet. Even then, 6,000 years. The tyranny of distance doesn't care about our ambitions. It doesn't matter that Kepler-22b might have liquid water, might have a stable climate, and might be the most habitable world we've ever found. None of that changes the fundamental reality that it's unreachable with anything resembling current technology. Habitable does not mean accessible. Remember the light we discussed earlier, the photons that left Kepler-22b 635 years ago and arrived at our telescopes in 2011. We can see that world. We can analyze its atmosphere. We can study its star and calculate its climate. We can imagine what standing on its surface might feel like, but we can never touch it. Not in our lifetimes. Not in 100 lifetimes. The distance isn't just a problem to solve. It's a barrier that redefines what's possible. We've found a world that might support life, a planet in the habitable zone with the right temperature and possibly the right conditions. And it might as well be in another universe for all the good it does us. 992,000 years at our fastest speed, 6,000 years at theoretical maximum. Those aren't engineering challenges, they're civilizational impossibilities. But numbers on a page don't capture the true scale of what we're discussing. 635 light years, 992,000 years. These are abstractions. To understand what this distance really means, we need to make it tangible. We need to feel the void between here and there. Let's try something simple. Walking speed, 3 miles per hour. That's a comfortable pace, the speed you'd use to cross a park or walk to a store. 3 miles every hour, 72 miles every day. About 26,000 miles every year if you never stopped. Kepler-22b is 635 light years away. That's 3.7 quadrillion miles. At walking speed, 3 miles per hour, never stopping, never sleeping, never dying. The journey would take 241 billion years. The universe is 13.8 billion years old. Walking to Kepler-22b would take 17 times longer than the universe has existed. You couldn't start this walk at the Big Bang and finish it today. You'd need 17 Big Bangs worth of time. The journey isn't just impossible, it's temporally impossible. There hasn't been enough time in existence for a human being to walk there. Let's try something faster. Highway speed, 60 miles per hour, the speed you drive every day. You get in a car when the first humans pick up stone tools and start shaping them. 2.5 million years ago. You drive without stopping. No sleep, no fuel stops. Just endless driving at 60 miles per hour through empty space. You're still driving today, right now, and you've covered about 10% of the distance. 90% remains. You'd need to drive for another 22 million years to reach Kepler-22b. Stone tools to spaceflight got us 10% of the way. Maybe flying would help. A commercial airliner, 500 miles per hour, fast enough to cross an ocean in hours, fast enough to circle the Earth in 2 days. Imagine an airplane leaving Earth 66 million years ago. The moment the asteroid hits, the moment the dinosaurs start dying, the airplane takes off and never lands. It flies through the extinction event, through the age of mammals, and through the rise of primates and the emergence of humans, through every civilization, every empire, every war. It flies through the invention of the airplane itself, and it arrives at Kepler-22b right about now. 66 million years of continuous flight, every second, every minute, every day, for longer than anything with a backbone has walked on land. And that's still slow, absurdly slow. Let's try the fastest thing humans have ever built. The Parker Solar Probe reaches speeds of 430,000 miles per hour when it dives close to the Sun. At that speed, you could reach Mars in days. You could reach Neptune in months. You could cross the entire solar system in a year. The journey to Kepler-22b would take just under 992,000 years, nearly a million years, long enough for human evolution to run its entire course twice over, long enough for continents to shift and ice ages to come and go, long enough for everything you know to become dust and myth and forgotten history. That's our fastest machine, 430,000 miles per hour. And it's not even close to fast enough. Light doesn't have this problem. Light moves at the ultimate speed limit, 670 million miles per hour. Nothing in the universe can move faster. Light crosses the distance from the Sun to Earth in 8 minutes. It reaches Pluto in 5.5 hours. It escapes the solar system in less than a day. And light takes 635 years to reach Kepler-22b, the fastest thing in the universe. The thing that defines what fast means, 6 centuries. Yet the photons arriving today left that world in 1388, before the printing press, before Columbus, before telescopes existed to see them arrive. Those photons traveled for longer than the United States has existed as a nation, longer than most empires last, longer than most languages survive. 635 years at light speed. That's not a travel time. That's a barrier written into the structure of reality. The universe sets a speed limit, and even at that limit, the journey spans civilizations. This is what 635 light years means, not as an abstraction, not as a number on a page, but as a lived experience translated into speeds we understand. Walking takes longer than time itself. Driving takes millions of years. Flying takes longer than complex life has existed. Our fastest spacecraft takes 1 million years, and light, the absolute fastest anything can possibly go, takes 6 human lifetimes. The void between here and there isn't empty space waiting to be crossed. It's a gulf that makes the crossing meaningless. You can't walk there. You can't drive there. You can't fly there. You can't even think your way there fast enough. The distance rewrites what possible means. Human beings live maybe 80 years. Civilizations last a few thousand. Our species might survive a few million if we're lucky. These numbers don't intersect with the travel times. They don't even come close. The journey to Kepler-22b exists on a timescale where human concepts like effort and determination and progress stop having meaning. But maybe time and distance aren't the right way to understand this gap. Maybe we need different comparisons, different ways of making the invisible visible. Let's try measuring this distance in different ways. Not speed, not travel time. Something more human, something we can feel. 635 light years equals about 3.7 quadrillion miles. That number doesn't mean anything. It's too big. But imagine you started counting those miles. 1 number per second. 1, 2, 3, 4. Just counting. Never stopping. Never sleeping. You'd count for 95,000 years straight. That's longer than writing has existed. Longer than agriculture. Longer than permanent cities. Longer than any human endeavor you could name. The surprise runs deeper. If you started counting when anatomically modern humans first appeared, you still wouldn't be done. Our entire species has existed for about 300,000 years. You'd need to count through the rise of humanity, the ice ages, the invention of language, the spread across continents, the birth of civilization, the entire written history of our species, and you'd still have 40,000 years of counting left. The distance to a nearby exoplanet can't be counted in a human lifetime. It can't be counted in 100 human lifetimes. It can't be counted in 1,000. Think about heartbeats instead. Your heart beats about once per second when you're calm. Every beat pumps blood, keeps you alive, keeps you thinking. A human heart might beat 3 billion times in a full life. That's 3 billion individual moments of staying alive. Take every heartbeat from every human currently living on Earth, 8 billion people, while 3 billion beats each. That's 24 quintillion heartbeats. Sounds like enough to count the miles to Kepler-22b, right? It's not even close. You'd need every heartbeat from every person alive, and then you'd need to multiply that by about 150. Every pulse of every human heart currently beating on this planet, times 150. Or go backward. Take every ancestor you've ever had, Every heartbeat they ever took, every breath, every thought that crossed their minds during their entire lives, all of it together wouldn't fill the journey time to Kepler-22b. Remember that 2.8 million year travel time from earlier? That's every generation of your family tree going back to when our ancestors were barely recognizable as human. Yet you'd need dozens of complete evolutionary lineages to fill that span. Not just your family, not just your species. Multiple branches of the evolutionary tree, from early hominids to modern humans, played out again and again. What does it mean to find a world we can describe but never visit? A place we can mathematically prove exists but will never touch? The light we see from Kepler-22b left when printing presses were exotic technology. That photon is older than every book in your house, older than every library. It traveled through empty space while empires rose and fell, while continents were discovered and mapped, while humanity went from wood and iron to silicon and uranium. The photon didn't age, didn't slow down, just moved through the dark at the only speed the universe allows. And when it finally arrived, when it finally struck a telescope mirror and got counted, it was still carrying information from a world 6 centuries behind us. Think about historical spans. 635 years ago, the Renaissance hadn't started. The Americas were unknown to Europe. The scientific method didn't exist. Islam's golden age was ending. The Ming dynasty was just beginning. Gunpowder was spreading. The printing press was 50 years away. That entire span of human progress, from then to now, is how long light takes to cross the gap, one way. This is the mathematics of unreachable things. Not abstract calculations, not numbers on a page, but human-scale measures that reveal the gulf. You could count every grain of sand you've ever walked on. You could measure every step you've ever taken. You could track every word you've ever spoken, and none of it approaches the scale of the distance. The gap doesn't just exceed human timescales, it exceeds human comprehension. We are trapped by distance just as surely as we're trapped by gravity. Earth holds us with its mass. Space holds us with its emptiness. The void between stars isn't a road waiting to be traveled. It's a fundamental barrier written into the structure of reality. Light itself takes lifetimes. Matter takes eons. And we, caught between the two, can only point our instruments and look. But maybe that's enough. Maybe looking is all we need. In 2015, NASA announced they'd found the most Earth-like planet ever discovered. Not Kepler-22b, a different world. Kepler-452b, 1800 light-years away in the constellation Cygnus. It orbits a star so similar to ours that you could swap them and barely notice the difference. The planet sits in the habitable zone, just like Earth. It receives sunlight at almost the same intensity we do. Its year lasts 385 days. Our year is 365. The match is close, closer than anything we'd seen before. The planet is bigger than Earth, about 1.6 times our diameter. That makes it a super-Earth, straddling the line between rocky worlds and gas dwarfs. We can't see its surface directly, we can't measure its composition with certainty, but the models give it better than a 50% chance of being rocky. Solid ground, real terrain, maybe oceans, maybe continents, the kind of place that could, in theory, support the chemistry of life. Gravity would be different. About twice what we experience here. Picture firefighters in full gear, heavy boots, thick coats, oxygen tanks, that weight they carry all day, every day. That's what standing on Kepler-452b might feel like. Exhausting at first, your legs would burn, your back would ache, but humans adapt. Over generations, bones would thicken, muscles would strengthen. Our ancestors evolved stronger skeletons when they climbed down from the trees and started walking upright. The same process could happen again, just in reverse. Heavier gravity pressing down, bodies responding over thousands of years. But here's what makes Kepler-452b different, what makes it haunting. Its star is old, 1.5 billion years older than our Sun. That star has already lived through Earth's entire future. Every year that lies ahead for us, every million-year chapter waiting to unfold, that star has seen it. Looking at Kepler-452b isn't just looking at another Earth, it's looking at what will become. Stars age, they brighten. As fusion continues in their cores, the reactions intensify over geological time. Slowly, imperceptibly, they grow hotter. The Sun is 30% brighter today than it was when Earth formed. In another billion years, it will be brighter still. And that extra energy accumulates. 10% more stellar energy doesn't sound like much, but spread it across deep time, and it's like slow cooking a planet. Each million years adding heat, like turning up a dial one notch. The changes compound. Glaciers shrink, oceans evaporate, atmospheres thicken with water vapor, trapping more heat, accelerating the process. Kepler-22b is already there. Its star has entered the phase our Sun is heading toward. The planet receives 10% more energy than Earth does. Not enough to boil the oceans overnight, but enough to set processes in motion. Processes we're watching happen in real time, 1800 light-years away. The models say Kepler-452b has about 500 million years before it hits a runaway greenhouse effect. Venus style. The oceans will boil, the atmosphere will fill with steam, water vapor will rise to the upper atmosphere where ultraviolet light splits it apart. Hydrogen escapes to space. Oxygen binds with surface rocks, while what's left is a thick blanket of carbon dioxide and a surface hot enough to melt lead. The most Earth-like planet becomes the least habitable, and Earth is on the same path, just behind. Our runaway greenhouse will start in 1 to 2 billion years. The timeline is longer, but the destination is the same. We're watching our own ending play out on another world. Think about that. The planet that resembles ours most closely isn't a twin. It's a preview, a dying twin. This isn't abstract. It's not a hypothetical future we can ignore because it's so far away. It's happening right now. Light left Kepler-452b during the early Middle Ages, and it's arriving here today, carrying information about a world in slow collapse. By the time we see what it looks like now, in the year 2025, and another 1800 years will pass. We're always looking at its past, but that past is our future. You could send a probe. The fastest spacecraft we've ever built, Voyager 1, travels at about 17 kilometers per second. At that speed, reaching Kepler-452b would take 2.8 million years, longer than our species has existed. You'd launch it, and the probe would still be traveling long after humanity either evolved into something unrecognizable or went extinct. It would arrive at a dead world, if it arrived at all. The most Earth-like planet we've found is one we'll never reach. And even if we could, we'd arrive to find a cautionary tale written in stone and steam. A world that was, perhaps, habitable once. A world that might have had its own chance at life, but now it's cooking under an aging star. There's something almost poetic about it. The closest match to home is a mirror showing us our end. Earth won't last forever. Neither will the Sun. Neither will any star or planet in this galaxy. Kepler-452b is just further along the arc. It reminds us that habitable doesn't mean eternal, that even perfect conditions are temporary, that every world, no matter how Earth-like, is on a clock. The search continues. There are other planets out there, worlds orbiting different kinds of stars, stars that age differently, burn longer, offer more time. Not every solar system follows the same script. Not every star ages like the Sun. Some burn cooler, dimmer, longer. Red dwarfs, the M-type stars, are the slow burners of the galaxy. They're smaller than our Sun, fainter, and they'll outlive almost everything else in the cosmos. They can burn for trillions of years, long after stars like our Sun have gone cold. Red dwarfs sound unimpressive, small, dim, prone to tantrums, but they're everywhere. The galaxy is full of modest stars, hosting modest worlds, and we're just now learning to notice them. In 2014, Kepler found something remarkable, orbiting one of these dim stars, a planet 500 light-years away, in the constellation Cygnus, Kepler-186f, the first truly Earth-sized planet ever discovered in a habitable zone. Not bigger, not smaller, just about 10% larger than home. The distance is staggering in human terms, 500 light-years. Even traveling at 90% the speed of light, the journey would take 550 years. You wouldn't make it. Your children wouldn't make it. Yeah, your great-great-great-great-grandchildren's children would arrive, and they'd never have known the Earth you left. They'd be born into a ship. They'd die on a ship, and only their descendants would see the destination. Kepler-186f orbits a red dwarf that's 25 times fainter than our Sun. 25 times. That changes everything about what life on that world would experience. Midday wouldn't look like midday here. It would look like Earth about an hour before sunset. Permanent twilight. The sky would glow a deep orange-red, casting long shadows that never really disappear. Plants couldn't photosynthesize the way they do here. They'd need different chemistry, different pigments. Instead of green leaves capturing our Sun's yellow light, you'd see darker vegetation, maybe deep purple or black, as soaking up every photon from that dim, red star. The whole landscape would look alien under that perpetual dusk. The planet receives about 1/3 the heat that Earth gets from the sun. That's Mars-like cold. Mars is a frozen desert because its thin atmosphere can't trap warmth. But Kepler-186f might have a thicker atmosphere, dense enough to hold heat like a greenhouse, warming the surface despite the low light. If it does, liquid water becomes possible. If it doesn't, the world stays frozen. We don't know which version exists. That's the honest answer. We can measure the planet's size and its distance from the star. We can calculate the heat it receives, but we can't see its atmosphere yet. We can't know if it's temperate or frozen. Both are possible. Red dwarfs have another problem. They're prone to flares. Massive eruptions of radiation that blast their planets without warning. These flares can strip away atmospheres over time, sterilizing worlds that might otherwise support life. Kepler-186f orbits far enough out that it might be safe from the worst of these tantrums. The habitable zone around a dim star is closer in than ours, but this planet sits near the outer edge, far enough to avoid constant radiation storms. Maybe. Think about the paradox here. Red dwarfs live longer than any other type of star. They give life trillions of years to evolve, to flourish, to spread, but they also bombard their planets with radiation during their violent youth. Any life that emerges would need to survive the storm first. Then it gets eons of stability. It's a brutal filter followed by endless time. And here's what nobody tells you about red dwarfs. They make up over 70% of all stars in the galaxy. More than 7 out of every 10 stars you could point to is a red dwarf. That means most planets in habitable zones orbit these dim, temperamental stars. Not bright stars like our sun, not stable, yellow, middle-aged stars. Red dwarfs. If life is common in the universe, most of it doesn't see a sky like ours. Most of it lives under a sunset that never ends. Most of it evolved under a star that barely glows. Our bright yellow sun is the exception, not the rule. We're the outliers. We live in the unusual case. That realization shifts everything. We've been searching for planets around sun-like stars because that's what we know. That's what feels familiar. But the galaxy doesn't care what feels familiar to us. Yet it's full of red dwarfs. And those red dwarfs have planets. And some of those planets sit in habitable zones. Worlds like Kepler-186f. These aren't the Earth analogues we imagined. They're colder, darker, stranger. But they might be habitable. They might host life. And there are so many of them. Billions of planets orbiting billions of red dwarfs. Each one a possibility we're only beginning to explore. Kepler-186f was the first Earth-sized planet found in a habitable zone. The first proof that planets like ours exist around stars. Nothing like our sun. It opened a door we didn't know was there. Behind it, a galaxy full of dim worlds under dim stars. Worlds we'd never considered. Worlds that might be teeming with life adapted to darkness. The search doesn't end with red dwarfs. There's a middle ground between these dim, temperamental stars and our sun. Stars that burn longer than ours but brighter than red dwarfs. Stars that might offer the best of both worlds. Orange dwarfs, K-type stars. They sit between the sun and red dwarfs on the stellar spectrum. They burn cooler than our sun but hotter than red dwarfs. They shine longer than our sun but brighter than red dwarfs. They might be the sweet spot for life, the stars we should have been searching around all along. These stars live for 15 to 45 billion years. Our sun will last about 10 billion years total. That means a K-type star could host a civilization that rises, falls, rises again, and the star barely ages. Complex life took 3.5 billion years to evolve on Earth. On a planet around an orange dwarf, you'd have that much time 3 or 4 times over. Evolution could take wrong turns, dead ends, mass extinctions. The star would still be there, steady and bright, waiting for the next attempt. The sun has brightened by about 30% since Earth formed. That change drove climate shifts across billions of years. Orange dwarfs brighten only 10 to 15% over their entire lives. Climate stability measured in billions of years, not millions. A planet in the habitable zone stays in the habitable zone. The conditions that allow life to start are the same conditions that allow it to become complex, to build civilizations, to develop technology, to look up at the stars and wonder. K-type stars avoid the problems that plague both ends of the spectrum. They don't swell and die young like sun-like stars. And they don't flare and strip atmospheres like red dwarfs. They're stable, they're long-lived, they're just bright enough that planets in their habitable zones aren't tidally locked. Those worlds could spin freely, creating day and night cycles, weather patterns, Seasons, maybe. The kind of dynamic environment that drives evolution forward. 1100 light-years away in Lyra, there's a planet called Kepler-22b. It orbits a K-type star. The planet sits right in the habitable zone. Its habitability index is 0.84. That's one of the highest scores we've ever calculated. Higher than Earth's, depending on the model you use. The planet is about 1 1/3 times Earth's size. It receives about 2/3 the light Earth gets from the Sun. Cooler, yes, but not too cool, not too hot. Right in the range where liquid water could exist on the surface. We don't know if Kepler-442b has water. We don't know if it has an atmosphere. We can't see it directly. The planet is too far away, its star too dim. What we know comes from the dimming of starlight as the planet transits, from calculations about mass and orbit, from models that try to predict what conditions might be like on a world we'll never visit in our lifetimes. Getting there would take about 1.7 million years with current technology. Picture counting. 1 number per second, never stopping. You'd count for 32 years straight just to reach the journey time in seconds. And that's just counting the seconds, not traveling them, not living through them. 1.7 million years is longer than humans have existed as a species. We'd have to become something else entirely before we arrived. The surprise is that K-type stars might actually be better for life than Sun-like stars. We've spent decades building telescopes designed to find planets around G-type stars. Stars like ours. That's what felt logical. That's where we expected to find life. But the logic was backward. We weren't searching where life was most likely. We were searching where we already knew life existed, around a star like our Sun. It's like losing your keys in a dark alley, but searching under a streetlight because that's where you can see. There are more K-type stars than Sun-like stars. Not as many as red dwarfs, but still billions in our galaxy alone. Each one burning steadily for tens of billions of years. Each one potentially hosting planets in stable habitable zones, or worlds where life could start, survive, and evolve without the star brightening too much or flaring too often. Worlds we've barely begun to search. The best stars for life might not look like our Sun. They might be smaller, cooler, orange instead of yellow. We got lucky. Our Sun has been stable enough for life to flourish. But that doesn't mean it's optimal. It just means it was good enough. K-type stars might be better. More time, more stability, more chances for something to emerge and look up at a sky lit by an orange star. Kepler-442b won't be the last planet we find around an orange dwarf. It's one of the first we've studied carefully. One of the first we've recognized as potentially habitable. As our instruments improve, we'll find more. Smaller planets, planets in tighter orbits, planets with atmospheres we can analyze. We'll start asking not just if they could host life, but what kind of life they might host. The galaxy doesn't care what we find convenient. It doesn't build planets around the stars we prefer. It builds planets everywhere, around young stars and old stars, around bright stars and dim stars, around stars that burn fast and stars that burn slow. Our job isn't to decide which stars should have habitable planets. Our job is to look, to find what's actually there, to adjust our expectations based on reality, not comfort. Orange dwarfs might be the real jackpot, the stars where life has the longest runway, the most stable conditions, the best chance to go from chemistry to biology to complexity to consciousness. We've been looking in the wrong place. Not entirely wrong, just not optimal. The universe has been patient with us. The planets are still there, waiting to be found. Some of those planets might be water worlds, oceans covering entire surfaces. No continents, no land at all, just water, kilometers deep, wrapping around a rocky core. 1,200 light-years away, there's a star with 2 planets that might be entirely covered in water. No land, no continents, no islands, just ocean, wrapping around a rocky core, kilometers deep. This is the Kepler-62 system. 2 worlds in the habitable zone, both potentially wet, both potentially home to something alive. Kepler-62 orbits its star every 122 days. That's roughly 4 Earth months. The models suggest it's warm there, humid, cloudy. Think of it like living inside a sauna that covers the entire world. Perpetual tropical humidity, water vapor thick in the air, clouds rolling over an ocean with no coastline to reach. The second planet, Kepler-62f, takes 267 days to complete an orbit, almost 9 months. It's farther out, cooler. It might need a strong greenhouse effect to stay warm enough for liquid water. But if the atmosphere is right, if the composition works out, it could be habitable too. Scientists use something called the Earth Similarity Index to compare exoplanets to home. It's a scale from 0 to 1. 0 means nothing like Earth. 1 means identical. Kepler-22b scores 0.83. That's one of the highest scores we've found. Kepler-22f comes in at 0.69. Still respectable. Still in the conversation. These aren't abstract discoveries. They're places, real worlds, orbiting a real star right now. If you could somehow send a radio signal to Kepler-22, it would take 1,200 years to arrive. 1,200 years. A message sent when Vikings roamed Europe would just now be reaching those planets. That's faster than any spacecraft we could build, and it's still measured in the lifetimes of entire civilizations. Water worlds sound peaceful until you realize there's nowhere to stand. Imagine explaining real estate on a planet with no estate. Beachfront property means something very different when the beach is the entire world. The question isn't just whether these planets have water. We're pretty confident they do. The question is whether they have any land at all. Yet computer models suggest that planets with the right mass and the right amount of water could be entirely ocean-covered. No peaks breaking the surface, no shallow regions, just deep water, all the way around. That creates a problem. Not for life. Life could thrive in those oceans. Complex life. Maybe even intelligent life. The problem is for civilization. Fire doesn't work underwater. You can't smelt metal. You can't make glass. You can't practice chemistry the way we do it. No forges, no kilns, no furnaces. Every technology humans have ever built starts with our ability to heat things up in open air. An aquatic civilization could be just as intelligent as humans, maybe more so, but they'd be permanently trapped. Intelligence without technology. Minds that could understand physics but never build a rocket, never even signal us. And no way to generate radio waves. No way to leave the planet. No way to reach beyond their ocean. Picture dolphins with human-level minds but no hands to build with. That's the reality of a water world. You could have philosophers down there, mathematicians, beings who understand their planet orbits a star, who grasp the concept of other worlds, but they'd never touch the stars. They'd never even see them clearly through the water. We assume intelligence leads to technology. That's the pattern on Earth. Humans got smart, then we built things. We went from stone tools to spacecraft in 10,000 years. But that progression requires a very specific environment. It requires land, air, fire. A water world breaks that assumption. Intelligence could evolve there. Social structures, language, culture, maybe even science, are passed down through generations, refined over millennia. But it would never become visible to us. We scan the galaxy for radio signals, for signs of technology, for evidence of civilizations that can build transmitters. A water world civilization wouldn't register. They'd be invisible, silent, not because they're primitive, but because their environment won't allow the tools we're looking for. The universe might be full of intelligent species we'll never detect, not because they're hiding, not because they're too far away, because they live on worlds where technology as we understand it can't exist. Think about what that means for our search. We've been listening for decades, scanning frequencies, looking for patterns in radio noise. We assume that any civilization advanced enough to communicate will send signals. But what if most intelligent species live underwater? What if the galaxy is teeming with minds that can't reach out? We'd be surrounded by intelligence and never know it, alone in a crowded cosmos. Not because life is rare, because the kind of life that can build transmitters is rare. There's a counter-argument. Nature is clever. On Earth, creatures leave the water even when it seems impossible. Flying fish evolved to glide above the surface. Amphibians crawled onto land. Evolution finds a way to exploit every niche. Maybe on a water world, life would find a path to technology, floating platforms, biological structures that rise above the waves. Some workaround we can't imagine because we've never needed to solve that problem. But maybe not. Maybe some barriers are absolute. Maybe fire is non-negotiable for the kind of technology that leads to space travel. Maybe we're only able to search for life because we got lucky, because Earth has continents, because we evolved on land where we could burn things. Kepler-22b and F aren't confirmed water worlds. We can't know for certain what their surfaces look like, because the models suggest deep oceans, but models are just educated guesses. We'd need to visit to know for sure, or at least get detailed spectroscopy, study their atmospheres, look for biosignatures, signs of life in the chemistry. That work is coming. The next generation of telescopes will be able to analyze exoplanet atmospheres. We'll search for oxygen, methane, combinations of gases that only make sense if something is alive. We'll build a catalogue of worlds, dry ones, wet ones, planets with land and planets without. And if we confirm that some planets are entirely ocean, we'll have to sit with an uncomfortable truth. We might never meet our neighbors, not because the distance is too great, though it is, because some neighbors can't build phones, can't send letters, can't reach across the void no matter how much they might want to. Intelligence trapped in an ocean, knowledge that can never leave the surface, civilizations that live and die without ever touching another world. That's not a failure of those civilizations. That's just the luck of planetary formation. Where you're born determines what you can become. On Earth, we were born in the right place, close enough to a star, on a planet with land, with an atmosphere that lets us see the sky, with resources we could mine and melt and shape. We didn't earn that. We got lucky. And somewhere out there, 1,200 light years away, something else might be just as smart as us, looking up through water at a sun they can never reach. In 2020, a team of scientists went back through Kepler's data, not the good data, the rejected data, the signals that the computer had flagged as false positives, and noise in the system, things that looked like planets but probably weren't. They were looking for mistakes, things the algorithm got wrong, and buried in the discarded files, they found Kepler-22b. It was real, a planet almost exactly Earth's size, orbiting a red dwarf star 300 light years away, receiving 75% of the sunlight Earth gets. Not too hot, not too cold, right in the habitable zone, and it had been sitting in the trash folder for years. Think about that. We might have already found Earth 2.0 and just didn't know it. How many other perfect candidates are hiding in datasets we ignored? How many worlds did we scan past because the algorithm wasn't sure, or because the signal was messy, or because no one had time to check? The census we're conducting isn't just incomplete. Parts of it are still in the filing cabinet, unread. Kepler-1649c orbits its star every 19.5 days. 2 weeks and you've lived a full year. Seasons flicker like a strobe light. Childhood lasts months instead of decades. Everything that takes us years happens in weeks. Growing up, aging, watching the stars turn. If you lived there, you'd celebrate your birthday more often than you currently celebrate the weekend. The planet has a neighbor, Kepler-1649b, 8% larger, closer to the star, too hot for life as we know it. The two planets orbit in a 4-to-9 resonance. For every 4 times the inner planet goes around, the outer one goes around 9 times. Planets dancing in mathematical harmony. That kind of resonance doesn't happen by accident. It suggests a hidden third partner we haven't seen yet. Something pulling on both worlds, keeping them locked in step. A ghost in the data that hasn't revealed itself. That third planet might be there. We just haven't found it. Or maybe we have, and it's in another rejected file, waiting for someone to look twice. Here's the number that should keep you awake at night. Based on everything Kepler found, there's a 95% chance of a true Earth twin within 20 light years of us. Not a maybe Earth, not a super Earth or a mini Neptune or a planet we're guessing about. A twin, same size, same temperature, same kind of star, same distance from that star. The real thing, 20 light years. That's closer than any planet we've discussed. Closer than Kepler-22b, closer than 452b, or 186f. Our nearest possible mirror is still 4 years away at light speed, still unreachable with any technology we have or will have in our lifetimes. But it's there, probably, statistically, somewhere in the neighborhood, cosmically speaking. Just not reachable, not by us, not by anyone alive today, or anyone they'll ever meet. The Kepler mission taught us something fundamental. Planets are common, not rare, not special, common. Almost every star has them. Most stars have multiple planets, and a significant fraction of those planets sit in the habitable zone, places where water could be liquid, where temperatures allow chemistry to get complicated, where life, if it starts, might survive. We've confirmed over 5,000 exoplanets. We've identified thousands more candidates. And that's just from staring at one tiny patch of sky for a few years. 1/400th of the whole sky. A porthole view. If you scale that up, the Milky Way probably contains billions of Earth-sized planets in habitable zones. Billions. Not scattered across the universe, just in our galaxy. The math is overwhelming. We're not looking for a needle in a haystack. We're looking for needles in a needle factory. Earth-like worlds probably exist in the millions. We just can't get to them, can't visit, can't send probes, can't even get a clear picture most of the time. We know they're there the way you know there are fish in the ocean, even if you've never seen one. The evidence is everywhere once you know how to look. What does it mean to find a world we can never reach? I think about this sometimes. The answer isn't nothing. And it means we're not alone in type, even if we're alone in practice. It means the universe makes places like home. It means Earth isn't a miracle. It's a pattern that repeats. Kepler-1649c is 470,000 years away at our current speeds. You'd need 20,000 generations to get there, 20,000 chains of parents and children living and dying on a ship aimed at a dot they'll never see grow larger. And when they arrived, if they arrived, they'd find a world that might look like home, or might not. We can't know until someone goes, and no one's going. That's where we are. We've mapped the neighborhood, we've counted the houses, we've estimated how many have lawns and driveways, and the right kind of light coming through the windows. But we're standing on our porch, looking out, unable to cross the street. We've counted the worlds now. Kepler-22b, where gravity would crush you before you could take a breath. Kepler-452b, Earth's future, written in a present. We can observe but never visit. Kepler-186f, dim and red, a world of endless twilight. Kepler-442b, circling an orange dwarf in what might be the universe's sweet spot. Kepler-62e and F, the water worlds, oceans without bottoms. Kepler-1649c, hidden in data for years, waiting to be found. Each one unique, each one fascinating, each one impossible to reach. We are cartographers mapping lands we'll never visit, astronomers naming stars we'll never touch. The universe has given us eyes but no legs. Finding Kepler-22b is like discovering an entire continent through a keyhole. Yet you can see it, describe it, even measure it. But the door is welded shut. You know there are mountains there. You know there's weather. You know light falls on whatever surface exists beneath those clouds. And you will never stand there. Neither will anyone you know. Neither will anyone they know. Stretching forward through generations until the names and faces blur into abstraction. That feels like a tragedy at first. We've spent 50 years finding these places. We've catalogued thousands of them. We've estimated their temperatures, their sizes, their orbital periods. We've calculated which ones might have water, which ones might have atmospheres, which ones sit in that narrow band where life as we know it could exist. And what do we have to show for it? A list, a catalogue, and numbers in a database describing places we'll describe forever, but never touch. But here's what that catalogue tells us. Here's what those numbers mean. There's a 95% chance that a twin of Earth exists within 20 light years of where you're sitting right now. 20 light years. That's close by cosmic standards. That's the neighborhood. We haven't found it yet because we haven't looked everywhere, haven't pointed our instruments in every direction with enough precision. But the statistics don't lie. The math is clear. It's there. Earth is not a miracle. Earth is not a rare pocket of habitability in a hostile universe. Earth is a pattern, and patterns repeat. The existence of unreachable habitable worlds isn't a limitation. It's a gift. It tells us we live in a universe that makes homes. Not just one home. And not just our home. Homes plural, scattered across the galaxy like houses on a street we can see, but not walk down. The universe makes places where water can exist as a liquid, where atmospheres can hold heat through the night, where the light from a star falls at just the right intensity to allow chemistry to become complex, and complexity to become something more. We are not special, we are common, and that's the most profound discovery we could have made. Those photons from Kepler-22b, the ones that left its star 635 years ago, traveling since the pyramids were still being built, reached us not as a road, but as a postcard, a message from a place that will never send visitors and will never receive them. Light carries information across distances we can't cross. That's all we get. And that's all we've ever gotten. And somehow, impossibly, it's enough to tell us we're not alone in type. Maybe that's enough, to know we're not alone in type, even if we're alone in practice. To know that out there, 635 light years away, an ocean might be catching light from a sunset that never ends. And we found it. We who've only been looking up for a cosmic eye blink found it. That counts for something. The light from Kepler-22b continues its journey through space. Right now, this moment, photons are leaving that system, carrying information about a world we'll describe but never touch. In 635 years, they'll reach Earth. Someone will be here, hopefully. Someone will build a telescope. Someone will point it at that star. And they'll see what we saw. A dip in brightness. A shadow. Oh, a world. And they'll wonder, like we do, what it would be like to go there, and they won't, and that will be okay, because knowing is enough. Knowing has to be enough. It's all the universe offers across these distances. And it turns out, when you really look at what we've learned, that knowing changes everything. It tells us where we are, not isolated, not rare, not alone in type, just here, on one world among many, looking out at a universe full of places we can see but never walk. And somehow, in that limitation, there's a strange kind of peace.